Okay, so welcome back. We are now going to be talking about the polarity of molecules. So let's just do a super quick review of what we did in our last notes, right? We have covalent bonds. I'm just going to write that over here. So covalent bonds are between nonmetals only. And we have two different types of covalent bonds. We have nonpolar covalent bonds, and we have polar covalent bonds. Actually, I want that to go from over there, not over there. So I'll make that look like a prettier, well, sort of prettier arrow. All right, so polar and nonpolar covalent bonds. So from this point forward, you really need to be a careful reader, and you need to ask yourself if a question or if something is referring to the bond or whether or not something is by the molecule. So underneath my bar over here, which I don't know if I figure out how I can move that somewhere else. I don't really know if I can move that somewhere else. Hide floating meeting controls. Oh, okay, so there, I did it. I learned something new today. Okay, so how the polarity of a molecule is determined. So we have the bonds, and now we're going to have something which is a molecule only. So a molecule is made up of the bonds, but the bonds themselves can be polar or nonpolar. So remember, nonpolar, the word polar means different. So then a polar bond is between different nonmetals, right? So two different things that are considered nonmetals on the periodic table. And nonpolar means not different means the same. And this is going to be between the same nonmetals. So the same nonmetals. So like example of Br2, right? Because two bromines together are two of the same. That's a nonpolar covalent bond. And now we have polar. So like that would be like hydrogen with bromine, two different nonmetals. So the bond between them is polar or nonpolar. And so now let's talk about what does that mean in terms of molecules. So when I think of in terms of molecules, right? So molecules are made up of bonds. And let me turn on my little remote thing here. Okay, so it's the shape of a molecule that is going to determine whether something is nonpolar or polar. But please keep in mind, polar is still going to mean different, right? And so if we're looking at the shape of a molecule, if I see something that's different, and I'll explain more what that difference means. It means how the bonds are distributed around the center atom. That's going to be determined whether or not a molecule is going to be polar or nonpolar. So we have polar molecules have an asymmetrical shape. What does asymmetrical mean? It means not symmetrical. So that if you're looking at lines of symmetry, there's going to be differences, right? So polar meaning different. And unequal, right? So unequal, different. Distribution of bonds, right? So an unequal. So now let's take a look at what I mean here. So if I have a line of symmetry, two lines of symmetry, one line of symmetry does not make something symmetrical. If I have symmetrical lines, right, and I have my X and Y plane here, my X, Y, Z, right, in 3 dimensions, oops, sorry, then that's going to be what we call a polar molecule. So polar is going to be asymmetrical, right? So polar is different, asymmetrical distribution of charge around a central atom. So here would be my central atom, for example, and then the charge distribution, right, is going to be either pulled along your different axes, right? So we can have charge is being pulled, right? Because it's due to electronegativity differences between atoms. In which part of the molecule are the electrons going to be closer to? That's going to be where our distribution of charge comes. So now let's look at an example. What do I mean? So sometimes these things make more sense when we look at examples than just by giving out like some terms and some definitions. So if I have two different elements, that's going to be polar, right? It's going to be a polar bond. So right, this is a polar bond because I have two different nonmetals. Now let's look at our symmetry between them. So if I draw this line of symmetry, I have a hydrogen on one side and a chlorine on the other side. This is not symmetrical. This is asymmetrical. So it's not symmetrical So this is going to be a polar molecule that has made up of a polar bond. So that would be our linear example of a polar molecule made up of polar bonds. So remember, bond, which elements are getting together. Molecules has to do with our shape. Right? In chemistry, shape is one of the driving forces of how things behave chemically and physically, as is in biology as well. Now let's look at something that has a bent shape with two different elements again. So again, here is water, right? So here's H2O. This is HCl. And if it is 2 hydrogens to 1 oxygen, oxygen being my center atom, let's look at symmetry here. So if I draw this line of symmetry, I have 2 hydrogens above the line and I have no hydrogens below the line. This is not symmetrical. So then we call this also polar. Now I'd like to say, what does this mean, right? So we are talking about charge distribution. So we have positive ends and negative ends of our molecule. Remember our delta partial positives and partial negatives? So in this hydrochloric acid here, sorry, my super sensitive pen here, we have a pull of the electrons in this direction. So there's more electrical charge, and here is my partial negative charge, and here is my partial positive charge. So across this bond, right, we have an unequal, so we have a pull, a little pull by the hydrogen, big pull by the chlorine, makes that charge distribution asymmetrical because it's kind of leaning towards that chlorine. Now let's look at the charge distribution. Oxygen here is our partial negative because it has a higher electronegativity, plus it has all those lone pairs of electrons. And we have our partial positives. And so when we talk about charge distribution, like if you know what vectors are, this has to do with vectors. So then I have a charge getting pulled closer in this direction, right? There's more pull in that direction. That's the way the electrons are hanging out. And those two vectors cancel each other out in any way. So that's not symmetrical. So then these are polar molecules due to their shape made up of polar bonds. And so now we have something that's called a pyramidal. And so now we're looking at our lines of symmetry, still not symmetrical. And here we have nitrogen surrounded by 3 hydrogens, right? So here is our ammonia molecule, right? This is NH3. And here is my 1 bond. There's the second bond, there's the third bond, right? So our partial negative is going to be over here with the nitrogen, and I have my partial positives over here with my hydrogen. So that if I have a pull and a pull and a pull, right, it means that there's going to be an asymmetrical distribution of charge. So it's not distributed evenly. So it is a polar molecule. And again, this is a polar bond because I have 2 different non-metals. And this is considered the shape of a pyramid, which looks kind of like. All right, so let's keep moving on. And so notice I have, without a number, that's a 1. Without a number, this is a 1. Without a number, this is a 3. Notice these are like odd numbers. That's like a little clue without having to, oh, you're never going to be in doubt if you draw it. But if you end in an odd number, if your last element, sorry, so element, if your element ends in an odd number, subscript, it's likely to be, it's going to be polar. It's not going to be symmetrical. All right, there's our center atom. So now let's look at the opposite. So nonpolar. Nonpolar means not different. If polar meant asymmetrical distribution of charge, nonpolar has to be the exact opposite. So that's going to be an even distribution of charge, symmetrical. And then we have an equally distributed charge around the center atom. So let's look at a linear molecule. So here I have hydrogen, right? So here is our H2. Now what type of bond is this? So in this bond, I have 2 of the same nonmetals. This is a non-polar bond. And it also is a non-polar molecule, right? So non-polar both. And all of our Brinkelhoffs or Hofbrinkel or your 7-Up diatomic elements, right? I like the Brinkelhoff, right? Or Hofbrinkel. right? These are our diatomic elements. Our diatomic elements are all linear molecules. They have nonpolar bonds. They make nonpolar molecules because of their shape, right? I have an equal pull in this direction and this direction, right? So those two factors cancel each other out. So that means even distribution of charge. Right? No matter which way line of symmetry we draw, that hydrogen linear molecule, it's the same on both sides. Everything is equally the same. So that's going to be symmetrical. Now let's look at something in a tetrahedral. So tetra, right, is the prefix that means four, right? So it's basically a four-sided pyramid, right? So you've got your three sides and the fourth side being the bottom plane. And this is going to be, let's see, this is one of the most popular ones. This is CH4, which is methane. Notice this ends in an even number. Notice this ends in an even number, and they're all the same. So if I'm doing distribution of charge, then I have carbon is getting the stronger pull than the hydrogen. So these are all pulling this direction, right? So then this vector cancels out this vector cancels out this vector. If you like to think in terms of math and vectors, vectors become more important as you get on into like in physics, but let's look at just drawing lines of symmetry. So is it symmetrical on the top and the bottom? Yes. Is it symmetrical from left to right? Yes. Oops, let me go backwards, sorry, too fast. So then this is also a symmetrical distribution of charge. This is symmetrical. So it is nonpolar. So this is a nonpolar molecule. Now let's look at the bonds, right? If I have carbon and hydrogen bonded together, these have polar bonds. So all the ones that are nonpolar bonds will also be nonpolar molecules because of the shape, just basically just the way they are designed. But when we have polar bonds, right, which means two different nonmetals, they can arrange themselves in such a way that they become symmetrical. And not all of them can do this, but when they arrange in a symmetrical way, we have a nonpolar molecule because it means not different. So when I draw the line of symmetry, there's nothing different, not different. Draw the line of symmetry, not different. So then there's a little memory trick that I have to remember this, and let me change color so it stands out. Let's go with purple. Yeah, let's go with purple. Well, actually, let's go with red. So red always stands out, right? So I like to remember this is whenever you have a molecule, you need to snap, right? Molecule polarity is a snap, which stands for symmetrical is nonpolar, asymmetrical is polar, right? Bonding is a snap. Molecules are a snap. If it's referring to a bond is always which two elements are getting together. In this case, is the hydrogens. Two hydrogens together, not different elements, they're the same. Nonpolar bond, symmetrical, nonpolar. Now I have a polar bond because I have two different nonmetals, but when they arrange themselves and I draw it out as my Lewis structure, it is symmetrical. Notice with the even numbers and the odd numbers, if you're just given a bunch of formulas, you can predict with a great deal of confidence whether or not it's going to be symmetrical or non-symmetrical, right? So if I have SO2 or CO2 for that matter, these are going to be also polar bonds, right? Because sulfur and oxygen are different, carbon and oxygen are different. And now let's look at the subscript of 2 means that I have just two things. These are also going to be non-polar molecules. And we'll do lots of practice with drawing these and identifying them. And the best way to do it is keep practicing and you'll get better at it. In our next video, we'll talk about metallic bonding. Thank you.